raise that to have A to be sigma plus A, and then A dagger is sigma minus A dagger. So we have product of the forms something like this. So this is sigma plus sigma minus A dagger minus sigma minus A dagger A. Okay, so that's our commutator right there. And evaluate this commutator, we start from what we know, right? So this, we know this can be written as A dagger A plus 1. We should be familiar with how this works out by now. Okay. So that allows us to write this as sigma plus sigma minus, okay, plus sigma plus sigma minus minus sigma minus sigma plus A dagger A, something like this, right? Okay. So what is the commutator between sigma plus and sigma minus? Sigma z, right? But really, we don't need to remember that because this, for the two-level system, this is very simple. This is like E, G, G, E, right? So this is just, if I write it out in the two-level representation, okay, what is this? This is just this. Okay, because this is 1, so 1, and you just have E. And then similarly, this is just G, G, which is, obviously this gives you the sigma 3, right? Okay. So we get that the Hamiltonian is equal to okay. So that's our result. And as I was saying earlier, and what's special about this Hamiltonian is that you see that the number operator appears here. So this Hamiltonian is not dependent on A or A dagger alone, it's actually dependent on the product, which is the number operator. So this kind of interaction preserves the number of photons, which is what we've been saying all along. It's a dispersive interaction where there's no absorption or emission, because the fields are all resonant. So this is this. So now let's think about how this will evolve the state, because the state will evolve roughly according to this time evolution operator. Right? And we have some states written in the interaction picture that you should understand this part. And then e to the minus I h effective over h bar. So let's consider some composite state with some composite state of the field and the atom. Think about if we started with the atom in the ground state and the field in some number state. Okay. But if we started with this, so what is this time evolution going to do to it? First of all, this is just E, so this does nothing to the ground state. Over here, there's going to be a minus GG, right? Okay. And this reads off the number. Okay. And then remember the whole, oh, I forgot the chi here. H bar chi, right? Correct? Okay. So the whole thing is like, you have some specific frequency chi, you multiply it n times and you get a minus sign. So basically, psi of t is going to be e to the minus I, oh, there's a minus sign here, so which cancels this minus sign, which is, if I resolve this into e minus g kind of thing, there's a minus sign here. So this is a plus in the end. G, correct? Okay. That's how the ground state and a number state evolves. What about the excited state? Okay. Let me call this the ground. Side of T excited. Well, first of all, you're going to pick up a 1 from here, which contributes to 1 chi. Right? And then over here, you're going to pick up n times chi, n times 1. Okay? So totally, in total, the field is going to be rotating with chi, n plus 1 chi, and we have this minus sign here. So e to the minus chi, n plus 1 chi. Okay. So by themselves, these are not very interesting. If the atom was initially in the ground or excited state, which means that the atom is already in one of its eigenstates, then we see that it keeps in these eigenstates, but just acquires these phase factors. These phase factors by themselves are not measurable, which is to be expected because right now we neglected the possibility of a transition between the atom and the photon, and the field. So if the atom is sitting there in an eigenstate, it should sit there. And this is just introducing this field is kind of like setting a reference for the energy or something. We basically change the total energy inside of the field. We just change the total energy inside of the cavity. And if I change the total energy, I get a reference in the energy which is just picks up a phase factor, right? But notice how, first of all, for the ground and excited state, the states are rotating. If I neglect the difference between n and n plus 1, the states are rotating in opposite direction, right? So you can have some interesting physics happening if we consider a bunch of number states with different ends, which later we'll consider this coupled to a coherent state. But first of all, let's just consider an atom initially prepared, maybe in one of the blocks, the Bell states. Okay. What if I have an atom prepared into 1 over square root of 2 E plus G? How do we prepare this? Right. We use a James-Cummings model with the resonance field. And if I have the atom coupled to a number state in a resonance field, okay, it's going to undergo Rabi oscillation. And if I control the coupling time, right, the Rabi oscillation gives me a cosine factor and a sine factor. If I control the time so that we have a pi over 2 or something pulse, remember if you're pulse, so Rabi oscillation is cosine something theta over 2. And then the other one is sine theta over 2. Right? So if I control the time which is related to theta, okay, if I control theta to be pi over 2, I can have this state. Right? So by subjecting my atom to a, let's consider something like this. You have a source for atoms, okay, which is maybe an almond or something. You subject this to some first cavity. And the cavity has omega naught, which is exactly resonant with the atomic transition, E and G. Okay, so this is the resonant EG transition. And I will say that this pulse is theta equal to pi over 2, which according to Rabi oscillation gives you 1 over square root of 2 this kind. So at this point, right, we have this state. Okay. So now I further send this atom into some other cavity, which is at omega c, and omega naught minus omega c is my detuning factor. And now I'm in the dispersive interaction, dispersive loop. Okay. So now, what's going to happen in here? Okay. So obviously, I'm going to get a superposition of these two things. Right? So I can psi of t, okay, which is the t, the time t is the time the atom spends in here, okay, in this cavity. Psi of t is equal to 1 over square root of 2. Well, e goes to this thing, so e to the minus I m plus 1 pi 2 plus e to the I m pi 2. Right, that's the whole thing, atom and field. Okay. Okay. So now, let me subject this to another cavity, another resonance cavity. So here it is omega naught again. Okay. Let me subject this to another pile of the 2 poles, which turns E to this, okay, and turns G to minus E plus G, something like that. So E is going to go to square root of E plus G, and the ground state goes to 1 over square root of 2 minus E plus G. Okay, something like this. So if I were to push some terms around, you can see that after leaving the third cavity, 1 over square root of 2, I have the excited state is going to be this minus this, right? E to the minus I m plus 1 pi t minus e to the I. And then the ground state has what? E to the minus I m plus 1 pi t plus e to the I m pi t. And then the field state is already factored out. So now if I make a measurement of the level of the atom, I can get either excited state or a ground state, but these are time-dependent coefficients. Now I just evaluate these coefficients. So 1 over square root of 2 here. Oh wait, no longer 1 over square root of 2, right? Because this square root and this square root gives you 1 over 2. So the probability to find the atom in the excited state as a function of time, okay, this is going to be 1 over 4, okay, e to the minus I 1 plus 1 pi t minus e to the I t squared. Okay, so what is this? Now notice this is minus m plus 1 pi t m pi t, right? So I can take out some phase factor and turn this into sine of m plus 1 over 2 pi t. So once I do that, okay, the sine squared is going to go into 1 minus cosine, 1 plus cosine squared. I mean 1 plus cosine 2, whatever is inside. So this is going to give you 1 over 2, 1 plus cosine of, I believe, 2m plus 1 pi t. Which is just a trig identity again. And then similarly for this one, there's a plus, so you get a cosine square. Cosine square goes to 1 minus the double angle. And the probability to ground state is 1 minus cosine. So a sanity check, these two sum to 1. At all times, so that's good. Okay, so what this is saying is, although the field remains in the end state, okay, but the number of photons in the field is going to determine the frequency at which we will detect the excited or the ground state. right? So by looking at it, if I do a measurement, if I have some setup like this, and I continuously send in atoms prepared in exactly what I want. So maybe over here, I am certain that the atom is in the excited state. Okay, so that needs some preparation by itself, but let me omit that part. So in the excited state for sure, okay, definitely going to be in one of these bell states, and then afterwards, so if I set up this experiment and I continuously feed atoms through this, okay, and I continuously measure what is the probability to find an excited atom and a ground state atom, okay, then I can, by fitting the data with a sinusoid, I can roughly deduce what is 2n plus 1, provided I can calculate chi from the given geometry and the given atom. Because chi is equal to lambda squared divided by delta. Right? Delta we know, okay, this is controlled by the detuning. Chi is equal, lambda is equal to dg divided by h bar. Yeah, something like that. All of these things can be calculated. G is based on the field mode in the cavity, okay? D based on the type of atom. So all of these factors can be calculated. So this gives you a way to measure the number of photons, okay, without actually destroying any of the photons. So yeah.
Interesting. How do you know the outgoing final state is E or G?
It's going to be in a superposition, right? But then I'm going to measure it. Yes.
So how do
The detector is just going to find out whether it's in E or G. What I can do is I can have some ionization thing, right? And if it's in the excited state, and I set the ionization energy to the excited and the vacuum difference, then it's going to be excited. Right? If I'm in the ground state, it's not going to be excited. So I can switch between these two states. Collect the data and fit these two curves. And so this is called, if you're really interested, you can look up Ramsey interferometry. Okay. And for their wide use, okay, these resonant cavities with these pi over 2 halls, and these are typically called Ramsey zones. Okay. And then this is the cavity where dispersive diffraction. So this is what happens. We can use this. We can use this effective Hamiltonian with a special property that it preserves the number of atoms, the number of photons. Okay, we can use this Hamiltonian to do quantum non-demolition measurement, okay, which is something that we've sketched over there. So now, let's consider Schrödinger cascades, which is what we get by considering the coupling to a coherent state. So by now you should have acquired this kind of understanding that the James Cummings model and the cavity is basically something that entangles the field and the photon and the atom, right? Okay. So if I have a cavity and I put field and the atom in it, under the James Cummings model, what comes out is an entangled state of both the field and the atom. So now what we're going to do is previously we've been entangling things like two spins, okay, or two atoms. It was like in the previous lecture we showed you how we can use cavity QE to entangle two atoms, right? And to prepare them in one of those Bell states. Oh, this is not a Bell state, I'm sorry. Yeah, this is not a Bell state, this is just a superposition. So now we're going to do something different, which is to entangle the state of a microscopic atom to the state of a classical field, which is a coherent state. Right? And we're going to arrange the parameters such that the two coherent fields in the entangled product is going to be distinguishable. Okay. So what this means is that if I now set this up, then the two distinguishable macroscopic states is going to be entangled to two microscopic states. So remember in Schrödinger-Katz experiment, or thought experiment, Schrödinger said, okay, if you take the Copenhagen interpretation seriously, okay, then you get absurdities like you can have a cat that is alive or dead and being in a superposition of those states. Right? So that's an absurdity. But today, not today, today and on Thursday, we're going to try to show you that that's actually not an absurdity because it's not so easy to entangle these things and keep them entangled. What you'll see is that you have entanglement at one point, and then the state as it evolves, because it's inevitably coupled to the outside environment. And once there's that coupling, okay, the entangled parts will die off. And when the entangled parts die off, okay, you basically have a density matrix that just looks like two classically superposed macroscopic states. Okay? So the cat either being surely dead or being surely alive, and the probability as a function of time are classical probabilities. Okay? Basically, you don't have the off-diagonal terms will die off in your density matrix. So this is what promotes people in studying these Schrödinger-Katz states, is to basically monitor the time decay of these coherence when you are able to entangle a microscopic system with a macroscopic state. So let me show you how we can do that. And first, let's consider what happens to a state like this. Okay, the ground state with the coherent state. So using that effective Hamiltonian, the ground state is going to give us just a sign, which is a plus sign pi, because of the what we have said. So e to the minus I h effective t over this a. And this is going to be e to the I. This is just using the ground state. Alpha e to the I. And why is that? So remember that for the free field, right, e to the minus I h field e over h bar. When this operates on alpha, I believe this was on your take-home exam, right? What happens when this operates on alpha? We replace the alpha by just its. We replace the alpha by e to the minus I omega t. Right? So now in this effective Hamiltonian, our omega is just chi. Right? And the ground state helps you to get rid of this minus sign. So this is what you get. Okay. What about the excited state? So first of all, okay, there is a term that's independent of the field. Okay, so we're going to get that as an extra phase factor first of all. So you get e to the minus I chi t. Okay, e, and then alpha e to the minus I chi t. Why is that? That's because in the sigma 3 state, the excited state has a plus sign. So that plus sign is going to help you pick up the minus sign coming from here, right? So this is what happens. Right? So now, what's interesting is that you have a coherent, for a ground state, for the atom in the ground state, the coupling gives you a coherent state rotating in this fashion. Well, for an atom, initially in the excited state, you have a coherent state rotating in this fashion. So why are these two coherent states different? Let me say that we can control the phase factor, the time that the atom spends in this non-resonant field, such that pi t is equal to we want pi. Okay. So what this is, if this is the case, then this gives you minus I, or yeah, minus I. Okay. E. Wait, that's not right. That's minus 1. Minus 1. Okay, something like that. So, whereas this one gives you plus alpha. So now, did we ever talk about what? That's also minus alpha. So this is we cannot yet entangle them so easily. Okay. So let me show you. Let me show you how we can entangle them. Again, we're going to need this setup, this kind of setup right here. But now let me consider a three level atom. Excited state, ground state, and there's some state called F here, okay, which is very far off resonance. So this one, let me call it omega R for now, and I'll show you why. And then this is again our omega naught. This is the delta thing, which is the detuning, and this is the field omega. Okay, so now our setup is again going to be something like that. Setup is going to be, again we have some atomic beam that's passing through the whole thing. Okay. And first we subject it to a Ramsey zone. And this Ramsey zone is coupled to omega R. Okay, so this is the S to G transition. Okay. So imagine in this zone, this one is off resonance reading, right? Okay. And what's dominant is this on resonance behavior between G and F, which is coupled, which is described by the James-Cummings model. Okay. And then we subject it to a pi over 2 pulse over here. Okay. So the atom is initially prepared in the ground state, in the G state. Okay, so at this point, it's going to be 1 over square root of 2 G plus F, right? Okay. So the second cavity that it experiences is some off-resonance cavity with omega, and the coupling is such that it couples the ground state and the excited state dispersively. Okay. But really only the ground state matter now because the excited state was not popular. And you see that again, even for the case of a coherent state, there's no transition. Ground state goes to ground state, the excited state stays in the excited state. And so this one. Whereas in the second cavity, because omega and omega R are so different, even the dispersive interaction is not important anymore. Because remember, the dispersive interaction is dependent on chi, which is inversely proportional to the detuning. Right? So for large detuning, we do not need to consider even the dispersive interaction. Okay, so delta lambda square something like that. Right. So in the second state, okay, basically, we enter the second cavity with 1 over square root of 2. So let me label some stuff. 1 over square root of 2, G plus F. And then this is directly in a product state with the coherent state in the middle cavity, this cavity. So nothing happens here, right? Because there's not even a dispersive interaction with these two.
Is it because we started with G alpha? How do we get the coherent state?
Oh, I mean, the coherent state is fed in externally. Okay, so we have prepared the cavity into some kind of coherent state. So now these things, this is going to evolve, but this is not. So now let me let this evolve by controlling the time that the atom spends in the middle, in the second cavity, to be so that thing was pi. Right? So that goes to G minus L. Okay. So I get 1 over the square root of 2 g minus alpha plus. Okay. So now the two things are just entangled. Okay. So using the second Ramsey zone, okay, and this has been the theme all along. Using Ramsey zones, we can get things to turn into a superposition. So perhaps true. Did we talk about the quantum quantum computing, and did we talk about the Hadamard gate?
Yeah, we did.
Yeah. So this is Ramsey zone is a realization of the Hadamard gate, where you take one state and rotate it to a superposition, right? To one of these even superpositions. So if I now pass this through a Ramsey zone or a Hadamard gate, okay, still coupled to omega r, which is the F to G transition, and I still use pi over 2. Okay, so F G transition pi over 2, something like this. Okay, I will get, okay. Basically, what I can do is I can take minus alpha coupled to and attach it to G, and then minus alpha plus alpha attach it to F, something like that. So I get 1 over 2 okay. G this would be minus alpha plus F, and then this is minus alpha plus F. Okay. Right. So now, if I subject the atoms to some kind of a measurement over here by determining whether it's in the F or G state, then I project the field in this middle cavity to a superposition of two coherent states. And did we talk about the phase space representation of coherent states? What I mean is this. So remember when we derive these coherent states and when we work with the operators, the way we constructed these non-Hermitian operators is A and A dagger. Right. This was by doing like x plus I p and x minus I p, something like this. Well, maybe with some kind of some factors over here. I can't remember. Maybe it's 1 over square root 2 or something. It's definitely going to be 1 over square root 2. Because we want A dagger A to be plus 1/2. This should be something like x squared plus p squared, right? Yeah, so I guess that would work. But then x and p come equal like h. So you need this h bar omega this plus 1/2. Yeah. So this works. And here the x and p are dimensionless. So instead of commuting to be h bar over 2, they commute as 1 over 2. Okay, so that's why you need to attach this factor here. That's how we arrive at this A and A dagger operator. Okay, so now if I in phase space, which is this P and this P and X space, okay, I can draw the coherent state, and it's going to span a circle located at somewhere. Because what we know is that the coherent state, this alpha factor, the alpha is an eigenvalue of the annihilation operator, right? And that eigenvalue is going to, in general, be complex. So if I expand that complex thing into its real and imaginary parts, then I can write that complex thing over here, right? Okay. But there's some uncertainty associated with this, okay, which gives me the spread. You can think about this as the uncertainty between x and p, which in a coherent state is the minimum uncertainty, or 1/2. Or you can think about this as the uncertainty in A and A that basically the commutation relation will give you a spread. Okay? And as time goes on, we know that alpha is replaced by alpha e to the minus I omega t. Right? So as time goes on, what happens to the coherent state is that minus omega would give the counterclockwise rotation. Yeah. So as time increases, the angle increases. So it's like this, right? Counterclockwise? I think so. Right, okay, so it's going to be centered with plus, minus is the other way. Anyway. So it's going to be centered around here. So that's what the coherent state does, and that's exactly what a classical oscillator does too. Right? Because if I project this circle onto these two axes, I get sine and cosine, which is exactly what the classical oscillator would do, going through sinusoidal oscillation. So that's how you make connection from the coherent state to the classical state. So now the two coherent states, alpha and minus alpha, one is over here, the other would be over here, right? Okay. So they are as separated as they can be. And the more separated they are, the more distinguishable they are. And when they are this maximally separated two coherent states, we call them macroscopically distinguishable. And there are statistical ways, which we will talk about on Thursday, to distinguish between these. And now we've constructed these two states like this. You either superimpose them oddly or evenly. Right? So these are called the even and odd cat states. And what we will talk about on Thursday is how these cat states decohere. Okay? And they will tell you that although it's possible, so I think about this as being the cat and the atom that controls the